In this video, we're going to take a look at another function, another program calling a function. In this case, we're going to be passing a parameter into it. So we got a simple program here that just reads a variable in, and then passes that variable as an argument to the function, which takes it as a parameter, declares a local variable, and then just does a simple little for loop to print out a number of asterisks, whatever number of asterisks I told it to. The other thing of note here is that it's using a global variable, which it's I don't know, to a certain extent it defeats the purpose of passing a argument, but it's not that unusual. And you can have global variables you want to pass around, global objects typically you want to pass around. But anyway, that's just it works for this example. So let's go ahead and look at the Pep8 code. So first there's the global variable, so it's global, so you're using a dot block 2. And then we're going to jump down to the main part to look at that first. So here's our main. We're doing a decimal input, typing in a number, we're loading that number into the accumulator, and the reason we're doing that is so that we can put it on the stack. So that's how all of our communication between functions work. We got to put it on the stack to be able to pass information back and forth. Global variables can be up in main memory, but once we get to the point where we actually want the functions to communicate back and forth, they have to put it on the stack in a known location so the function that's being called can get it off of that location. So what we're doing here is once that number that we entered at the keyboard is loaded into the accumulator, we store it on this with stack relative addressing here at a -2. So what that's technically doing is storing it. Remember the 2 or the number, the first part is the offset to the stack pointer. So it's actually storing it 2 bytes above what the current stack pointer is. Because if you remember, that doesn't the store doesn't really allocate any space. It's not until you get to the sub SP where we're actually allocating space. So I don't know, that might seem a little bit backwards, but there's actually some good reasons for it. I mean, it does help solve some problems later on, we'll see, but also it gives us some nice symmetry here, because the idea is we get everything in place on the stack, and then right before our call to our function, we allocate space on the stack, and then as soon as we come back from the function, we deallocate the space. Because there's other things we could put on the stack too. Well, if you think about it, if we wanted multiple parameters on there, it would get potentially messy if we put something on the stack, allocated space, put it on the stack, allocated space. So again, it's the way the compiler does it, and it's relatively efficient, so that's the way we're going to do it. We're going to store our parameter or argument here, because we're getting ready to pass it, above the stack pointer. Then we're going to allocate space, and then we're going to do the call. And if you remember, the call looks at this print bar, puts it on stores it in the program counter, saves the next address onto the stack. So now you have the parameter on the stack as well as the return address on the stack. And then we end up here up in our function. And remember, our function, back here for a second, remember our function also had a local variable inside there. So in our Pep8, we've got to allocate space for that local variable. So we have both, like we've been doing, we have our equate to say where it's going to be on the stack, and since it's the last thing we're putting on the stack, it's going to have the lowest number. It's going to be offset 0. And then we're going to allocate space with the 2. So really, local variables always start at 0. So if we had multiple local variables, I mean, if they were all integers, we'd be going up by 2s. If we had some characters in there, we'd be going up by 1s. But in any case, they always work the same. They always start at 0. The thing that's different here now is we are passing in this parameter, and it's on the stack. So if we look at our equates here, we've got the I at 0, and then the n is at equate 4. Now, if you think about that, our I is an integer, so if these were both local variables, the second one should be a 2. So why is it a 4? Well, it's because, remember, what the call did. The call put the return address on the stack too. So we put the parameter on the stack, then we put the return address on the stack, and then the function put the local variable on the stack. So the idea is if we start with the local variable in between these two, and you could actually, it's nobody typically does it, but you could actually put another label in here and actually say that return address was at offset 2. You'd never use it because you shouldn't really be changing that or doing anything with that, but it does. It's sort of a little marker there. So I'm not going to do it, but you could, and if nothing else, you can just think about it as you're doing it. But that's the point is you've got to make room for that return address in between there. And when I trace through here, we'll actually see the picture and we can actually see where it goes and get a little visual representation of it. So anyway, once we've got our local variable assigned with the equate and allocated, remember we don't have to do any allocation for the parameter because that was done back in the calling function. But then we run into our program and there's nothing special here, and it's a loop, and it's the stuff we've been doing. So, and you should walk through here and make sure you understand it. But for the purposes of this video, we're going to jump down here to, once we've done all our work in the function, we get down to our add sp, so we're at the end of the function. That's where we deallocate space for our local variable. And then we get to our return 0, and remember that's the thing that goes to the stack, grabs the return address, takes it off, and loads it into the program counter so that we can jump back down here. And then we come right after the call statement, we're back down here, and that's where we deallocate that space for the parameter we added on beforehand. So let's take a look at how this actually runs through. And I don't quite remember what state I run it in, so it left this in, so I'm going to reassemble and load, and then I'm going to do the debug here. So we're going to do the step-by-step debug. So first thing we notice is we already have our global variable down here because the global doesn't, it's not like the stack where it's being allocated at execution time. It's right there at the beginning. So we got our normal branch that's going to take us down into the main function, and then we're going to decimal input a number, and I'm just going to make it a 2 small number. So then we can actually see it load here into memory. So we can see it with our trace tag. We can also see it up here in memory. And then we load it into the accumulator. And now here's where we're putting it in the stack address area. Remember, it's not technically going on the stack until we do the sub SP, but it's going to be stored in that memory. So if we look at our stack pointer, it's FBCF. So I'm going to hit this little SP down here to move down to the stack pointer memory. And we see, all right, right now the stack is pointing right here. That's where my stack pointer is. So if I'm going to store this value at a -2, that means it's going to go over here to the left-hand side. And we can actually see there's already some things stored in memory, so we're going to overwrite whatever's there. So I'm going to do this store -2. Boom. So there, that right next to the stack pointer, that 0002, that 2 that I entered is getting stored in there in the stack. Now remember that it hasn't allocated any space yet. Technically it's not on the stack. It's just in the right area. And I can tell that because I can't see it down here in my stack trace. When I do this sub SP, that's when it actually allocates space, and that's when I can actually see the 2. So I've got my original 2 over here in global memory, and now I've got my 2 as a parameter loaded in here in the stack. So now when I call the function, remember the function call is going to put that return address on top of there. So now I've got my parameter, I've got my return address, and next thing I get is allocating space for my local I variable. Boom, and now that's there. So now I've got everything on the stack. And keep in mind we're reading this from the top down, so the top of the stack is essentially 0. So the local variable is up there at the top at 0, and then that return address is at 2. That's the thing that the call put on there, and then my equate 4, my n is at 4, which is right where it's supposed to be. So everything is nice and lined up. And then if I run through this, I'm just going to step through it quick. It's going to print out my first star. It's going to print out my second star. That's going to branch away, and then I'm down here to my add SP. So here's where I'm deallocating space for my I. So when I do that add SP, that I is going to go away. Now that it came off the stack, but it's still over here in the stack, and the value's still sitting there. That 2's still there. It's just that now the stack pointer is moved over. Same thing with the return address here. When I do this return 0, that return address is going to pop off the stack, but it's still sitting there in memory. And that's one of those, from a security point of view, that's one of those things you got to be careful about is as you're communicating back and forth in functions and programs, you can leave actual information around that the bad guys can poke at. So if we were like doing secure programming, we would make sure we zeroed all this out before we did anything. But anyway, doesn't matter here. We're not doing secure programming. We're just making it work. So anyway, we're back to the calling function. So we're right after the call. We do the add sp. So at this point, we're finally getting rid of that space that we allocated for this parameter. And at that point, all of our stack space is gone. So we've given back everything. And we're at the end of the program. There you go.